The ATM scenario, or automated teller machine, is an MM1 queuing theory problem. If you've downloaded the note frames, a copy of the MM1 formulas has been included at the back just for convenience. If you haven't, no problem, but that means you are going to need to look them up in a book in order to work this problem. Now, let's take a look at it. A single ATM is located on the ground floor of a shopping center. Okay, service time for the machine is exponentially distributed. On average, the ATM can serve a customer in 2 minutes. Customer arrivals at the machine are Poisson distributed with an average of 25 customers an hour. How was I so confident that this is the MM1 formula, other than the fact that it came with this formula sheet? The fact that it said Poisson distributed arrivals, exponentially distributed service time, and it's only one ATM machine basically makes it these formulas. Oh, okay, so we can calculate all kinds, we can learn all kinds of things about this bank machine, and there's all these different questions asked about the ATM by filling out these formulas. But we do need two parameters, lambda and mu. Now lambda is the mean of the customer arrival distribution, and that was spoken of directly right here. See that? An average of 25 customers an hour. That is perfect. How fast are the customers showing up? We need that number for our formulas. Then mu is its cousin, the mean of the distribution, say service distribution, and you see, and they said something here about an average of every 2 minutes, so mu equals 2. Don't write 2. Mu does not equal 2. One important aspect of the MM1 model we just want to always remember is that mu is never a length of time. It's talking about the average service or the distribution of service, but it's never a length of time. That's what we were given, this business about 2 minutes. Mu is always the average number of services that could be provided in a certain time interval. What time interval? Whatever time interval lambda's talking about. Okay, those two things have to match. So, what number in these formulas should we use for mu? Well, we were told that it takes on average 2 minutes for a customer to use the machine. There's 60 minutes in an hour. This is just logic. So 60 divided by 2 reveals that on average 30 people could use the ATM in an hour. Perfect. For the purpose of the formulas, that's the mu that we want to be using. 30. All right, now what was actually asked? What is the average number, or the average amount of time required to get money from this ATM in minutes? Okay, that's got to be on this sheet someplace. Average amount of time, it's going to be a W. And we have a choice. The average amount of time in the queue or the average amount of time in the system. The average amount of the time in the queue is the average amount of time you spend waiting. The average amount of time in the system is how much time you spend waiting and being served. It's like your total turnaround time. And here they're asking for in total to get money out of the machine, so they'd be asking for WS. So we need the formula for that because we're going to fill it out. So WS equals WQ plus, I'm just copying it over from the formula sheet, 1 over mu. You go, oh, well, wait a minute. But WQ is a formula. Yeah, okay, so we need that formula too. WQ equals LQ divided by lambda. But LQ is a formula. Yeah, so we need that formula too. LQ equals lambda squared over mu minus lambda. The MM1 formulas are like this. They kind of link together. So in order to answer this one question, the first part of the scenario, yes, we have to fill out all 3 of those formulas. We can do that, right? Go to the bottom of the list. Okay, LQ, the average length of the line, we have to calculate that first. Well, that would be 25 squared over 30 times 30, oops, not times 30 minus 25. Whoops. So I got 4.16667. So on average, there's a little over 4 people waiting for this ATM. Now, if you put that in your calculator and see this on the screen, just keep it on the screen. 0.1667, because we're going to carry this up here and say, and this is what you want to do next with the calculator, divide by 25. Divide by 25, because that's lambda. I get, all right, like 0.1666 runs on 7. Okay, that is the average weight for the machine. Now, weight, take this number. If it's on a calculator, put it in memory. But at any rate, we're carrying it up here because we want to now add 1 over 30, 1 over mu. So what you're going to get, and on the calculator you might see 0.1999999. Since we have a lot of repeating numbers, that's a very common result. But I mean, come on, it's not much rounding. It's really 0.2. Okay, so the average delay, the average amount of time it takes to take money on the machine is 0.2. Is that the answer? Actually, no, that's not the answer. Even though that's the result of the formula, that's not the answer. Because what is 0.2? It takes me 0.2 to get money out of the machine. It's 0.2 hours. One thing we have to remember about the formulas, the ones that return average waiting time or average delay, average some amount of time, they're speaking in whatever terms lambda and mu were speaking in. Remember, lambda was per hour, mu was per hour. The 0.2 is in hours, 0.2 of an hour. This problem, the question actually asks in minutes, so we are obligated to then multiply that times 60. I mean, it's easy to adjust, and that reveals, okay, 12 minutes. Oh, all right, so this bank machine, one thing we know about it is that if you want to get cash out of it, like you jump out of your friend's car and run over to use it, and you tell them, wait for me, I'm coming back, on average it's going to take you 12 minutes, all told. All right, so that one's done. Now, what's the next question? On average, how many people are waiting to use this ATM? Ah, perfect, that's LQ. That's a description of LQ, the average length of the line, or, and you know, I'll copy the formula over again here, but we already worked that happily for the first part, right? That's the, yay, 4.1. At least we got to use some of that work. 667. Okay, on average, a little over 4 people are waiting to use this machine. Oh, all right. Third question. On average, how many customers could use this ATM in an hour? Now, you might be thinking, okay, how many customers can use it in an hour? I'm going to look here on the formula sheet. Where is it? This particular question is so simple, it's a little tricky. The key is it's so simple. Wait a minute. On average, how many customers could use the ATM in an hour? It's not really a formula. It's asking for mu. That's what mu is. On average, how many customers could use the ATM in an hour? Or the answer to it is, you know, mu equals 30. On average, 30 people. Since it takes 2 minutes on average for a person to use it, then on average, 30 people could use it in an hour. There, answered. That one's done. Okay, next question. What is the probability that the ATM will be idle? Okay, probability of idle equals probability of no one in system. Now, why am I writing that? To relate it to how it's usually labeled on a formula sheet. See this? Probability of no customers in the system. Pretty simple formula. That's what we need. Capital P for probability, 0 for probability of nobody being there, no customers. It's just 1 minus lambda over mu. So 1 minus 25 over 30. I get 0.16667, or basically 16.7%. There's about a 16-17% chance, if you decide to go get money, that in fact when you show up it's not going to be anybody there. You can walk right up to the machine. Okay, good to know. Now, last question. By how much would the wait for the ATM improve if new technology could reduce the average customer service time by 30 seconds? Okay, now first off, what are they asking about? Wait for the ATM. That's WQ. Now, what are they proposing to change? Average customer service reduced by 30 seconds. Now, we were told originally that it was 2 minutes. Oh, and so what they're saying is what would happen to essentially WQ if instead of 2 minutes, this was 1.5 minutes, because 30 seconds is 1/2 of a minute. So we would be reducing it from 2 minutes to use the machine to 1.5 minutes. What part of this problem would be changing? Well, where did we use that 2 minutes? We used that in the calculation of mu, right? Our old mu, we said 60 divided by 2, we got 30. We sort of have a new mu now. 60 divided by 1.5. Our, put it in quotes, new mu, the new mu is 40 per hour. Oh, okay. Now, we haven't calculated anything yet, right? We're just exploring the question. So what they're essentially saying is if they could change right now, on average, 30 people can use the machine in an hour. And if they made this change, the result is on average 40 people could use the machine within an hour. And that's nice, but that's not what they asked. They asked what would happen to the wait to use the machine. Oh, so we can calculate, well, WQ is LQ divided by lambda, and LQ is lambda squared over mu minus lambda. We could essentially calculate a new WQ. But we can't do that until we calculate a new LQ, right? Oh, all right. Well, I can do that, right? It's just putting in, let's see, in the case of LQ, it would be the same arrival rate. So it's the same 25 customers for lambda squared. It's just that it's a 40 down here, and then 40 minus 25. I get 1.041667. So that's sort of interesting, because if you look back on the page before, when we were working on the problem at first, one of the things that we'd calculated and actually answered a question is we said, well, yeah, on average, there's about 4 people. 4 originally, 4 people waiting to use the machine. Now what we've done is we've speeded up how fast the machine can help people. We just shaved 30 seconds off of the service time, and we have concluded that, oh, look at that, now on average there's only about 1 person waiting to use the machine. Now, too bad that's not what the question asked, because then we would actually be finished. This is a means to answer the question. We need this number right here, because then we need to say this number, 1.041667, divided by, remember the lambda doesn't change, divided by 25. So I get 0.041666, again repeating. Okay, that's hours. It's not very intuitive. Take that, multiply it times 60 to translate it to minutes. I get 2.5 minutes. The new wait is 2.5 minutes. Okay, that's good. Now, have we answered the question? Well, what was the old wait? Uh-oh. What was the old wait? Wait, we were working on that. What was the old wait? The old wait, let me get a bit, aha! The old wait was this, we calculated that. The old wait was 1.6667. Okay, now the new one's 2.5 minutes. Oh, wait, the old wait, WQ, we never did translate into hours because we didn't have to. last time. We just didn't have to. We could do that, multiply that times 60, multiply that times 60, and that reveals that the old wait to use the machine was 10 minutes. Oh, right, because this is the old scenario. You waited on average 10 minutes, and it took on average 2 minutes to get cash out of the machine, so your total delay, and that's what we were after the first time, was 12 minutes. So the old wait was 10 minutes on average. The new wait is 2.5, so 10 minus 2.5, we have improved. That's just kind of was the definitive reading I wanted to answer this question. It does say by how much would the wait improve? It would improve by 7.5 minutes. It would go from, it was, and that's what we just had to check. Oh, it was 10 minutes, and it will go to 2.5 minutes, so it will improve by 7.5 minutes.